Dear colleagues, first let me wish you a nice day. My name is Boljianovic, Research Associate Professor, and I am coming from the Mathematical Institute of the Serbian Academy of Sciences and Arts, Belgrade. Please note that this research work is the result of my collaboration with Professor Andrea Carpinteri from the Faculty of Civil Engineering, University of Parma, Italy. Let me start with my presentation with title Fatigue Analysis of Quarter-elliptical Corner Crack. Load carrying capacity of mechanical structures may be often limited due to manufacturing and material flows, such as corrosion of pits, welding inclusions, coupled with aggressive environmental factors. Such stress concentrators, approximated as semi-elliptical or quarter-elliptical cracks, may seriously endanger the integrity of components due to formation of fatigue damages. Therefore, to provide safety performance of plate-type components, damage tolerance analysis has to be performed through relevant computational fatigue performance tools. The aim of this research is to develop computational framework for analyzing the failure mechanism caused by surface corner crack under cycle loading. Here are points that will be analyzed in this presentation. Fatigue resistance assessment for the plate with quarter-elliptical corner crack through residual life calculation and crack path simulation. Fracture mechanics analysis in terms of the stress intensity factor using analytical method and finite element method. The effects of geometrical parameters, crack shape thickness on the component life, cycle loading, and relevant applications of developed computational framework. The complex singular stress state field is responsible for the occurrence of fracture due to accumulation of damage in the vicinity of the crack tip. From the fracture mechanics point of view, such driving mode zone should be considered either in terms of stresses or displacement expressed by equations 1a to 1c and equations 2a and 2b, where stresses and displacements are generated through relevant functions of stress intensity factor. The identification of both the local failure modes and their occurrence in time represents the crucial information in order to avoid collapse over the structural life, which can be obtained by means of the stress intensity factor using appropriate analytical and numerical fracture mechanics models. The relationships related to the stress intensity factors for depth and surface crack growth directions are presented by equations 2 and 3, where FQECA and FQECB are the corrective factors related to the quarter-elliptical corner crack. Delta S is applied stress, A and B are depth and surface crack lengths, delta Ka and delta Kb are the stress intensity factor ranges for depth and surface direction. This slide presents relationships for the stress intensity factors and relevant corrective functions related to the plate with quarter-elliptical corner crack, in which the crack length in depth direction is shorter than such in surface direction. Where A and B are depth and surface crack length, T is the thickness of the plate, delta S and delta P represent applied stress and force. Delta K is the stress intensity factor. The detrimental effects of microconcentrators caused by stress gradient in the zones with initial flows can be avoided during service operations of structural components if such safety relevant mechanism is tackled through suitable fracture mechanics models. Thus, failure resistance analysis should be performed in terms of crack rate as a function of stress intensity factor range. The propagation of surface corner crack is tackled herein through crack growth rate in two depth and surface crack directions expressed by equations 5 and 6. In the frame of fatigue-resistant design, the number of loading cycles to failure is evaluated by integrating the crack growth rates for relevant initial A0, B0 and final AF, BF crack length in depth and surface directions. Bearing capacity of structural components with fatigue damages may be often threatened due to complex interaction between service loadings and environment. Such effect is here analyzed through the fracture mechanics parameter M expressed by equation 9, where R is the stress ratio, beta and beta 1 are material parameters experimentally obtained. Computational fatigue resistant model developed in this research work is presented in Figure 3. In the failure analysis of plate type configurations, geometrical and loading parameters associated with material properties are used to evaluate the driving forces along the crack front. Then, by employing suitable fracture mechanics concept proposed by Huang and Moi, the crack growth rate is evaluated. Also, the fatigue strength is assessed in terms of number of loading cycles in depth and surface crack directions. Moreover, the same crack growth concept was employed for evaluating the crack path under cycle loading. Now, some applications will be tackled in order to assess the predictive capability of developed computational fatigue performance framework. Firstly, fatigue resistance of dog bone configuration with quarter-elliptical corner crack shown in Figure 4 is theoretically tackled by means of the residual life. The failure analysis was performed by employing loading, material, and geometrical parameters presented on the left side of this slide. It is worth to be mentioned that cycle loadings with two different stress ratios R equal to -1 and 0 are herein tackled. Estimated number of loading cycles in the case of R equal to -1 as a function of depth and surface directions are shown in Figure 5AB and Figure 5CD for two different levels of applied stresses. Furthermore, for three different stress levels, the number of loading cycles evaluated through the developed framework is compared with those experimentally tested by Grover and colleagues. From the comparison shown in Table 1, it can be seen that evaluations correlate well with experiments. Now, for the same damaged configuration and stress ratio R equal to 0, the evaluated life versus crack length in depth and surface directions through developed framework is shown in Figure 6AB and Figure 6CD. Also, relevant comparisons tackled in Table 2 indicate that good agreement between different fatigue life results is obtained. Now, the failure strength of the plate with quarter-elliptical corner crack, shown in Figure 7, is evaluated taking into account the effects of the thickness and width of the plate. Relevant fatigue parameters related to loading, material, and geometry of the plate are shown on this slide. The evaluated number of loading cycles as a function of crack length in the case of three different thicknesses as well as three plate widths are shown in Figure 8AB and Figure 8CD for depth and surface crack directions. Comparisons presented in Figure 8AB and Figure 8CD show the thickness and width of the plate may rather threaten the residual strength of the plate with surface corner crack under cycle loading. Through this research work, the effect of crack shape is also taken into consideration. Thus, the failure in the case of three different quarter-elliptical crack configurations, B0 equal 0.9 mm, 1.5 mm, and 2 mm, is tackled through residual life by adopting loading geometrical and material parameters which are shown on the left side of this slide. For different initial crack lengths in surface direction, the evaluated number of loading cycles as a function of crack length related to the depth and surface directions is shown in Figure 10A and 10B. From such figures, it can be observed that the shape of crack-like flow may significantly affect the fatigue strength of the plate. The failure of the plate with quarter-elliptical corner crack subjective cycle loading, shown in Figure 11, is explored by means of stress state evaluations. Fatigue parameters related to the plate geometry, loading, and material are listed on the left side of this slide. In this research, since a part-through crack configuration is tackled, the singularity of stress field is analyzed through the three-dimensional finite element method. Thus, for different crack growth increments, the stress state field is numerically analyzed step by step through the stress distribution and stress intensity factor. A representation of the stress distribution in the case of crack length equal to A equal B equal 3.66 mm is shown in figure 12. Further, numerically obtained stress intensity factors are compared with those evaluated through equations 2 to 4, together with such employed to calculate relevant parameters M1, M2, M3, G1, G2, and FW as shown in table 3. Fatigue resistance analysis presented in this section evaluates the crack path for quarter-elliptical corner crack under cycle loading, shown in figure 13. The failure analysis is carried out using loading and geometrical parameters together with material properties, which are shown on the left side of this slide. According to the developed fracture mechanics framework, the crack path simulations are performed for initial crack length in depth and surface directions equal to 1.7 mm and 2.3 mm by evaluating relevant stress intensity factors and crack growth rates through equation 2 to 4 and equations 5, 6 together with equation 9. Modeled crack paths for 10 different depth crack lengths are shown through 5 calculated curves in figure 14a and 14b, where vertical and horizontal axes match with the front face and left edge of the plate. Finally, let me conclude. Among different sources of damage under cycle loading, fatigue due to crack-like surface flows is one of the most safety-relevant mechanisms in the plate-type structures. Thus, for this research work, a novel computational framework is developed for evaluating the performance of quarter-elliptical corner crack. The implementation of the Huang-Moix failure concept extended for surface flows, together with relationships for stress intensity factors, provide a good correlation with the experimental data. An important benefit of the analytical numerical framework presented is that it can assess the failure resistance under cycle loading simultaneously through residual life of component and crack path. Thank you very much for your attention.